In this video, Section 6.1, Definition of Functions, and Section 6.2, Composition. So, we'll start off with the definition. What is a function? Well, a function is a rule or a mapping that relates one set to another set. That's extremely general, but that really is all that we need for a function. We just need a rule taking one set to another set definitively. For example, let's suppose I've got my first set here, 1, 2, 3, and I want to map it to my second set here, A, B, C. I want to find a correspondence between these three numbers and these three letters. So I could say, oh, well, 1 goes with A, 2 goes with C, and 3 goes with B. And then this right here would be a function. It's limited in scope, but it still is. Now, what would make this not a function? If I had, say, 1 goes to A, 2 goes to C, or B sometimes, and 3 just doesn't go. I've got some problems here. First, 3 needs to go somewhere. It's in the set of numbers I'm interested in. So this number needs to be assigned something here. So I would just have to say 3 goes to A as well. Okay, I've fixed that problem. Now, here's my other problem. 2 is going to two different things. I don't know if 2 goes with C or 2 goes with B. I need a definitive answer. I need to say every single time I say 2, the result is B. Or even if the result is C every single time. I need to know every single time. There's ambiguity, and that's not good. So to fix this issue, we'd say get rid of the mapping to C maybe, and then we're good. But we don't have anything going to C now. That's okay. I don't need to cover everywhere I'm going. I just need a result for everything I input. Now, as far as notation is concerned, let's take a look at our example function. We have f of x is equal to x squared minus 16. And this is the other way that we could define a function. We could do it with an algebraic representation. And then over here we would have f, that's the name of the function, x, that's our independent variable, and then f of x, all of this together, that's our dependent variable. And what's nice is I have the independent variable expressed right in there. So for this function here, I could say look at f of 3, and then I would replace x with 3, so I'd have 3 squared minus 16, that's 9, minus 16, a negative 7. f of 3 is equal to negative 7. And right here, I have the name of my function, the input value, and the result. That's a very nice, compact way of writing things. Here's another example. Let's take g of x. We'll have this function be 3x plus 8. And we could find, say, g of 1. And that would be 3 plus 8, 11. I wonder. Could I take g of x and apply f to that? Could I look at, say, f of g of x? What would that look like? Well, instead of x squared, I'd have g of x squared minus 16. And g of x is, let's see here, 3x plus 8 squared minus 16. So this is 9x squared plus 48x plus 64 minus 16. So 9x squared plus 48x plus 48 is f of g of x. And commonly we would write that as f composed with g of x. So this right here is composition. It's when we apply one function to another function. Likewise, we could find g of f of x. We could find g composed with f instead of f composed with g. Let's see what we get. Well, that's 3 times f of x plus 8, which is 3 times x squared minus 16 plus 8. 3x squared minus 48 plus 8. That's 3x squared minus 40. Important thing to note here is that this is not f of g. The order in which we compose things is important. I'm kind of interested in something else here. I want to see if I can take g and find like an inverse of it. I should be able to find some way to compose g with an inverse. I mean, think about it. If I have x plus 5, well, and then I subtract 5, I get x. I have inverses here. So I'm hoping I can take g, I can compose it with some other function, we'll call it g inverse, and have the result be just x. And this would be the identity function right here. The identity function applied to x. So let's see here. I want to take g of g inverse. So that would be 3 g inverse of x plus 8. And I wanted the result to be x. Okay, so let's set it equal to x. Let's subtract 8 from both sides. I'll just try a little inverse reverse. And then divide both sides by 3. Okay, I have a function and I've solved for g inverse. I've just found the inverse of g. Cool. Let's try this again with f this time. F's a little bit more complicated, so this will be interesting. Alright, now remember, f of x was x squared minus 16. So f of f inverse of x will be f inverse of x squared. It's always good to, when you start squaring your functions, to put them in parentheses. Minus 16. And what do we want this to be? X. So we're looking for the inverse of it. Okay, well, let's go ahead and let's add 16 to both sides. I have f inverse of x squared is equal to x plus 16. And then square root. Okay, so move over here. F inverse of x will be square root of x plus 16. Oh, wait a minute here. It's a square root, plus or minus. Wait a minute, we have two solutions. So if I put a value in for f of x, say like f inverse of 2, is it the positive or the negative? This goes back to what we said previously. We need it to be definite, and that isn't. This is ambiguous. So this is not a real function. This is two separate functions. The positive is a function, the negative is a function. So maybe I'd say something like f inverse plus of x is equal to square root of x plus 16, and then f inverse negative of x would be the negative square root of x plus 16. So it's two separate functions. which means that there's no just inverse function for this guy. Okay, that's it for these sections. Thanks.